Welcome back to part 3 of this video. This is Billy. What I'm going to show you today is the full SOC lab, Kubernetes cluster, Splunk, Falco, network policies, detection rules, as code, SOC analyst, the whole thing. Built and deployed by Cloud AI multi-agents. Not assisted by AI, but actually built by that. One command, 6 stages. Each stage is handled by an agent that specializes at a task. And at the end, you get a working security operations environment with a live incident already in it. Let me just show you what it looks like when it's done. And then I will walk you through how it got there. Everything starts with one slash command /1 -soc -pipeline. There are 6 stages. Each one is a separate AI agent. They run sequentially. Each agent finishes, writes an adjacent state file, and the next one reads it before it starts. If a stage fails, the pipeline stops. You fix it, rerun, and it picks up where it left off. It's resumable. Stage 1, install K3s. That's the Kubernetes distribution with CIS hardening flags baked in. Audit logging, anonymous off disabled, kernel default protected. Stage 2 is the security hardening layer. OPA gatekeeper for admission control, Falco for runtime detection, Callidium for network policies, default deny everything. Then punch specific hosts. Stage 3 deploys the Splunk, the operator, the standalone instance, 4 indexes, hack token. Stage 4 wires up the log pipeline, Fluent bits ships container logs and audit logs to Splunk over the HTTPS. Falco sidekits forwards Falco alerts, CIM normalization so the fields are consistent. Stage 5 writes the detection. 8 Splunk SQL searches covering 8 minor attack tactics and converts all of them to Sigma rules for portabilities. Stage 6 is the SOC analyst. It deploys a privilege pod to trigger Falco, triage the alerts, writes the incident reports, builds the dashboards, and produce the final summary. So let me show you what it actually running. kubectl gets pods -a. You've got Splunk in its own namespace. Falco has a daemon set, 1 pod per node. Watching syscalls, Falco sidekits forward those alerts. Fluent bits also as a daemon set. Shipping logs. OPA gatekeeper, the audit pods, and the controller. Callidium for networking cert manager. The network policies, default deny everything. That explicit allows DNS API server access. Fluent bits to Splunk hack. Falco sidekits to Splunk hack. Nothing talks to anything unless it's explicitly allowed. Gatekeepers constraints, 4 of them. Block privilege containers, require resource limits, block host path mounts, block latest image tags. These are enforced at admission. If a pod spec violates any of this, it gets rejected before it even starts. Splunk itself, managed by the operator as a standalone custom resource. The operator handles the stateful set, the service, the secrets, the hack configuration. And let me show you the detection layer. The detection live here as a plain SPR files. 8 of them, each one maps to a specific minor attack technique. This one looks for privileged container creation in the audit logs. Verb is create. Resource is pods. And the specific has a privilege true. When that fails, it's a T1610 deploy container. And every single one of those SPL searches also exists as a Sigma rule. Same logic, portable YAML format. You can take this and run them on any SIEM, Elastic, Microsoft, Sentinel, whatever. The detection engineer agent wrote the SPL. The Sigma writer agent converted them. These are installed in the Splunk as saved searches. They run on schedule. When they fire, you get an alert. And why agents need guardrails? We'll find the stories. So here's the thing. The demo looks clean. One command, everything works, but that's not how it went in the first time or the second time. Let me tell you about some of the actual failures this project hit, and because they were the reason the harness exists. The Kuba bench job, that's a CIS benchmark scanner, got blocked by its own gatekeeper constraints. The job needs a host path mount to read the Kubernetes config. Gatekeepers block -host path -mount constraint said no. The agent had just deployed a constraint that was now blocking it. Fixed, exclude the Kubernetes namespace from the constraint before running the scan. Then remove the exclusion after. The Selenium DNS policy, the label format for core DNS in K3S is a K8S-app equal kuba-DNS with the K8S prefix. Without it, the selector doesn't match, DNS breaks cluster wound, and everything starts failing in ways that look completely unrelated to networking. Splunk, the operator version 3.0 requires an environment variable called Splunk_general_terms set to specific string to accept the license. Without it, the operator just silently refuses to reconcile. The port stays in pending. No error message that points at the license. You have to know. And Falco Sidekick, the webhook URL for the Splunk hack output had the 404 because the path format changed between versions. The agent was generating the URL from memory and getting it wrong. And the virtual machine IP. The IP address is not consistent. If the VM gets a new DHCP list, every hardbody reference breaks. The KDS-installer agent writes the node IP to its state file. Every downstream agent widgets from it instead of assuming. These aren't edge cases. These are the kind of things that can happen when you are wiring together 6 different systems that each have their own opinions about how things should work. The harness exists to catch them. Gate validation and state contracts. After every agent finishes, the pipeline runs the gate validator script. 3 checks. First, does the state file exist? If the agent crashed or failed early, the file won't be there. Second, is it valid JSON? A truncated write or a syntax error fails here. Third, does it matches the schema? Every state file has a JSON schema. Additional properties fails. No extra fields allowed. A required field listed explicitly. If the agent writes something that doesn't match, the gate fails, and the pipeline stops before the next agent reaches garbage. Here's a concrete example of why this matters. The security hardeners agents runs before Splunk exists. A Falco Sidekick, which it deploys, needs a Splunk hack token to forward the alert at stage 2. That token doesn't exist yet. So the security hardener writes a placeholder token to its state file. The Splunk installer reads that, deploys Splunk, generates the real token, and writes it to Splunk complete JSON. The lock pipeline agent that patches a Falco side kit with the real token. The schema for security hardener complete JSON requires a Falco side kit Splunk token field. So that handoff error occurred. The state catches it before the next page tries to use the placeholder as a real credential. And this is what makes the pipeline resumable. If stage 4 fails, stage 1 through 3 already have their state files. We run the pipeline, the gate validator sees those files, skips those stages, and pick up at stage 4. Config as code and destructive command blocking. Everything the agent built lives in configs. The agent don't generate YAML inline and pipe it to kubectl. They reference files by path. This is probably the single biggest error reduction mechanism in the whole project. When an agent generates YAML inline, it's working from memory. It gets a field name slightly wrong. It forgot required fields. It uses deprecated syntax. When it references file, the file is the source of truth. Reviewed, version controlled, and validated. The Carlilian network policies, the file went through several iterations to get the DNS policy right. The cross namespace hack traffic right to the two endpoints versus two services distinction. That knowledge is not locked in the file. The next run doesn't derive it. Now the other side of this. The agents run shell commands, and sometimes an agent, under the right condition, will try to run something it shouldn't. There's a pre-tool use hook wired into ClaudeCode settings. Before every single shell command executes, it runs a validate bash save with the commander's input. The script checks against the block list, rm-rf, mkfs, tables, and the systemctl stops k3s, k3s uninstalled. If the command matches any of these patterns, it exists non-zero and the command is blocked before it runs. This isn't about the agents being malicious. It's about the agents being wrong. An agent that's confused about its current state might try to clean up by removing something it shouldn't. The hook is a hard stop. Okay. Each agent in this pipeline has access to domain skills, files that get injected into the agent's context before it starts work. The KDS Debian 12 skill tells the KDS installer agents that it would otherwise have to discover on guess. That K3S on this kernel uses the container D socket /run /k3s /container D /container D sock, not the default Docker socket path. That the br_net filter and overlay modules need to load it before the K3s starts. Both modules must be present at K3s startup because K3s launches the container D as an embedded subprocess. If overlay is unloaded, the container D fails to initialize its snapshot store immediately on first run. K3s configures kernel networking parameters at startup. If br_net filter isn't loaded yet, that CTL doesn't exist and the write silently fails or errors out. that the kube config lands at /root/doc kube/config, even when the user is Kali. The KDS-hardening skills tells the security hardener that Falco on kernel 6.1.x should use the modern eBPF driver. No kernel module compilation needed. That's Selenium selectors for K3S system ports use the KAS label prefix. That gatekeepers constraints need excluded namespaces for system namespaces, or they'll block their own dependencies. Without these skills, the agents will hallucinate plausible sounding but wrong answers for these specifics. With them, they get it right on the first try. And when there's a memory system, each agent has a memory.md file that persists across runs. After a successful run, the agent writes what he learned, which driver worked, what the known issues were, and what not to repeat. Look at the entity. Kuberbench job blocked by own gatekeepers constraint. Run jobs in dedicated Kuberbench namespaces and patch all for constraints to exclude namespaces before running. And that's a hard one lesson from Will Sauer. Next slide. The agent reads this before they start and doesn't make the same mistake. Credentials never go into memory. The memory files are version controlled. They are facts about the environment and the system, not secrets. And one more thing that makes this work reliably, every command is idempotent. kubectl applied, not kubectl creates. Hem upgrade - install, not hem installed. Every resource creation is wrapped in an existence check. If the resource is already there, the command is null. Why does it matter? Because the agent fell partway through. Stage 2 might get through gatekeepers and Falco and that failed on Selenium. When you rerun, you don't want to try to recreate the gatekeepers resources that already exist and getting a conflict error. You want it to apply them, which is no-op if they are current. Move on to the thing that actually failed. This is what a resumption looks like. The gate validator checks KDS complete JSON exists, valid, passes schema, skips stage 1, checks security hardener complete JSON exist, valid, passes schema, skips stage 2, gets to stage 3, no state file, starts here. The combination of the idempotent command and gate validated state file means that you can rerun the pipeline as many times as you need to without worrying about duplicating resources or inconsistent states. Okay, let's wrap up. It's not a demo environment, it's actually a production pattern SOC stack, set as a hardened Kubernetes. Will network policies, will emission control, will runtime detection, will SIEM with normalized logs and schedule detections. But more than that, it's an argument about how to build a multi-agent system that actually works. The failures modes for AI agents aren't mysterious. They hallucinate environment-specific facts. They generate config inline instead of from files. They don't coordinate states between each other. They don't stop when something goes wrong. They repeat mistakes across runs. Every piece of this harness here addresses one of those failures modes directly. Skills inject the fact agents who would otherwise hallucinate. Config as code removes the inline generation. State files with schemas create a tight contract between agents. Gate validation stops the pipeline on failure. Memory files prevent repeated mistakes. The pre-to user hook blocks the commands that should never run. None of this is complicated. It's just a discipline. And the result is a 6-agent pipeline that deploys a complete security stack reliably, resumably, and without a human babysitting every step. The full project is on GitHub. Link in the description. The README walks through the architecture in details. If you want to run it by yourself, you need 16 gigabyte of Kali Linux, ClaudeCode, and Anthropy API key, and that's it. All right, that's a demo. Drop question in the comments, and I'll see you next one. And please subscribe to the video. Thanks.